All right. Welcome, everyone, to our Hypermatrix workshop. Good morning, afternoon, or evening, depending where you're connecting and when. It's a pleasure for me to have Richard Kerner with us here in Paris.
Hello, everybody.
Viktor Abramov, who's here in the Zoom meeting for later.
Yes. Hi.
Hello, Victor. And unfortunately, our second speaker wasn't able to make it today. He might be able to join later in the week. We'll keep you updated, but we'll have just a longer break after Richard's presentation, and otherwise the schedule is unchanged. So yes, I am very, very grateful for our host here in Paris, Richard, and obviously to Lyubov that has put a lot of work to have this room ready and everything to finally have this Hypermatrix workshop in person. So for all of you, those of you who don't know, last year we ran this purely online as part of the Wolfram Institute. So for those of you who don't know, the Wolfram Institute is a relatively new institution that has been started next to or adjacent to the science efforts of Stephen Wolfram and all the projects that have been done relating to this hypergraph rewriting systems and the sort of universe models that Stephen Wolfram was exploring with other collaborators a couple of years ago. And so we are now in the process of launching several research programs and continuing several research programs. And this is one of the efforts. So one of the research programs that I am involved with has to do with hypergraphs and adjacency information of hypergraphs, and this connected to hypermatrices. So we thought, let's bring the world experts on hypergraphs, tensors, higher order structures, higher arity structures and algebras together and have a discussion and a set of presentations. So here we are. So without further ado, I'm just going to give way to Richard, and we're going to hear from him about ternary and symmetry graded algebras.
Thank you.
So I'll mute myself, and then we can. Yep.
Let me put it here. Yeah. Hello, everybody. Thank you, Luba, and thank Carlos for having me here, and it's really a pleasure. And probably it will develop in something else, maybe more, even more wide and popular, we'll see. So as you see, the title is Ternary Z3 graded algebras. So the main goal is n-ary structures, but let us start modestly with binary and then ternary. It's already a step forward. So let's go. Let me see. Which one is?
Yeah.
No.
Space?
For space, should we start?
No.
You might have to click on the screen.
Oh, enter. No. Yes. Okay.
No.
Okay.
Oh, yeah.
Yeah. So space.
How did you do it?
Space.
Space.
So, pробел.
Just space.
To go back.
Yeah, and where?
This is back? No.
No, these are also.
Yeah, I think. Yeah.
Yes.
Yeah.
So that's back.
Ah, okay. Now it works.
Yes.
Thank you. So just to start with, this Z3 graded binary and ternary algebras were investigated in papers written in common with Viktor Abramov, Andrzej Borowiec, Bertrand Leroy, and Nadezhda Basunova. And most of the results concerning n-ary algebras were elaborated in '96 with Leonid Weinerman, and the generalized Z3 differential calculus was introduced in '91 and developed further with Michel Dubois-Violette and published in various papers. Of course, everything is an archive. So let me start with very modestly with a group of permutations or symmetric groups. Everybody knows it, but I like to start, kind of C infinity start with a very, very, very smooth stuff. So the groups of permutations, Sn, they just consist of all permutations, and the dimension of such a group is n. Is the how do you call it?
Factorial.
Factorial. Thank you. But cyclic permutations of n elements form an n-dimensional subgroup of Sn denoted by Zn, which is of course abelian. And the first non-trivial group is S2 group, which contains only two elements, the identity, like every group has an identity, and the other element whose square, so to speak, iteration is an identity. So this is one cyclic permutation. And of course, it is cyclic by definition. So S2 or Z2 are just the same. But this is no more true. Yeah, but let us speak about representations. The simplest representation of Z2 group is realized with action on complex numbers. And we have three different inversions that whose square is the identity element, each of them generating a different representation of Z2 in complex plane. So there's first, which is called the sign inversion, but this is not, again, it can be on the complex plane, it can be conceived as inversion, but it can be also conceived as a rotation by 180 degrees, which is not the same from the point of view of calculus, because inversion cuts really into two. But then you can, if it is just rotation, then you can go, then you can cut out only the positive line, and you still are in the simply connected space. Whereas if, for example, for next complex conjugation, you exclude the real line in a sense. And then the combination of both, which is just complex conjugation and minus sign. And of course, the fourth possibility is trivial representation. Everything is just, nothing moves, it's just the identity. So the problem is now, it's a little digression, is the covariance principle. That in order to adequately describe anything, you cannot stay with just collection of numbers. Collection of numbers, if you don't know how to translate it to another observer, to someone else, or if you change the basis, then it means nothing, it's meaningless. So you have also to define the transformation group that tells you how to transform this collection of numbers. It can be just components of a vector or a spinner or something to another observer, and then it becomes a geometric object. So this is, for example, I will give you the example, is Lorentz group, which tells you how to change the coordinates and time of one observer to another Galilean observer. So we know that it's given by a linear transformation. If you have two Cartesian frames, two Galilean frames, so it is given like you see, x mu gives you x mu tilde, which is a new collection of these four numbers, and they are related by an element of Lorentz group, which is here the vector representation, a 4x4 matrix, which acts on these coordinates. To be really strict, one should not use coordinates, but just differentials. Differentials are really linear. Coordinates may be linear or not. So, in fact, just you should look at this, I'll change it. The differential should be. The differential, this for sure, they transform like this. The coordinates may be curvilinear, so but usually it's one of the things that are persistently presented in any textbook or something, but written like this, it is too restrictive because it restricts to Cartesian coordinates, but you can have other coordinates. But the differentials, they are always linear and they are always subject to linear transformations. Okay. And now, if you have a field, now some other functions defined on this manifold, then you also are asking yourself what the components of these functions will be seen, how they will be seen by another. And then you need the representation theory. So the chosen representation, you see, you have to decide phi tilde of x tilde is somehow related with phi of x, the previous one. How the observer in first reference frame sees the field. And then this is the most important thing. This is called the covariance principle, that the new function of new collection of functions, new field of new coordinates can be expressed by the old field linearly. You see, by the representation of course, this new matrix, because it can be, the other one was 4 by 4, this one can be 2 by 2 or something, depends on the field, spinorial or something. And but it has to satisfy the representation properties. So S of lambda 1 multiplied by S of lambda 2 is S of lambda 1, lambda 2. I had forgot the big letters anyway. And S of lambda minus 1 is my S minus 1 of lambda. So this is the representation. Of course, this implies that S of identity is also identity. Now you have the same thing in quantum mechanics. I just repeat the same thing. This is for spinorial fields, how the spinors change under Lorentz transformation. So this is also well known. S is here the spinorial representation of the Lorentz group. And of course, the nature of this representation, I repeat again, it defines the nature of the field. It can be spinor or tensor, any field. So now I come back to our very simple case. There's the Pauli exclusion principle working in, by the way, I come back. This is something I would like to underline, because as usual, very, very simple formulas, behind them, you have something very, very deep. Not always, but often. Here, there's something very, very deep, indeed, because there are two completely different realms that are connected. One is space-time, the axis, the coordinates, what we observe by some macroscopic devices. And another is psi is an element of Hilbert space, of states. So it's this really completely different realm. It's the Hilbert space of states, of an electron, of an atom, of whatever. So you have the relationship between something that happens in space-time, macroscopically, and somehow it is related to what happens microscopically with the states in Hilbert space, which is not space-time. It's something completely abstract. It's a space of states. So this is very, by the way, Einstein's equations have the same property. They relate matter, which is quantum, with space-time geometry, which is classical. So again, you have this thing very deep. This is the problem, and of course, to solve this, it is still unsolved. How to imagine quantum gravity. So in the Hilbert space, there's, for example, for spinors, for fermions, you have a very simple principle. You cannot have the same state with the two electrons, for example. So this results in the anti-symmetry of the wave functions in the product of Hilbert spaces. You have two electrons, because they have spin, they have to have different spins. And the result on the wave function, which depends on two arguments, is that it must be anti-symmetric. So this means that in a Hilbert space of, say, of electronic states, you have an anti-symmetric anti-symmetric form. Again, now we'll apply, if we apply the principle of covariance to this statement, then we say that if we change the basis in Hilbert space, this principle has to be seen exactly, it should be the same. In the new basis, what was anti-symmetric should be anti-symmetric. But this means that if you change the basis with some 2 by 2 matrix, complex matrix, the new, as you see, epsilon alpha prime beta prime has to be exactly the same as epsilon. This is just the anti-symmetric form. So you see the equation, it's very simple. But if you look at what it tells you about this transformation, then you see that we write it down. For example, we choose and then you see that this means that the determinant of this 2 by 2 matrix complex matrix is 1. So, okay, I have a 2 by 2 complex matrix, which means that it is equivalent to 4 complex numbers or 8 real parameters. Now, how many real conditions do I have?
But it's not symmetric.
No, this equation, this is a condition, the unimodularity.
16?
No, there's only one equation.
Oh, 2.
2, because 1 is a real number, so the complex part is 0. So you have 2 real conditions on 8 numbers. What is left? 6. 6 is the dimension of SL2C group. Then you discover that it's the algebra, it's the Lorentz algebra. It's the same. So the Lorentz group is already present in electron states because of this covariant principle in Hilbert space. And then it is probably took up to our realm, and we observe, because if electrons are changed like this, the photons have to change like this too, and everything. So what is, we have the imprint of this, and we see whatever we observe with photons, we see always the same Lorentz group. Okay, so the covariance, now I come back to our problems, very simple ones. Covariance principle can be formulated in discrete case of permutation groups too. So for example, let us start with Z2. Consider the mapping of 2 indices into complex numbers. So our mapping is now not from space-time to some Hilbert space, but it's much simpler. It is the space of 2 indices into complex numbers. So it's like a matrix of 2 valence or 2 valence complex valued tensor. Now, under a non-trivial permutation of indices, this complex number, this image, can undergo, as we remember, there were just 4 different possibilities, 3 different combinations. So let us see. The trivial representation means that under the permutation, nothing changes. What you see in complex space is just unit operator. This is the trivial representation. But this defines symmetric forms. SBA equals SAB. Now, if we impose that inversion sign or rotation by 100, then we get antisymmetric tensor. Then the complex conjugation defines Hermitian tensors, because then you have the condition, the representation of permutation is HBA equals bar HAB. So this is called Hermitian. And finally, if you combine the 2, you get anti-Hermitian. So due to this unique separation into irreducible representation of a Z2, we get the irreducible separation of space of 2 forms into this different. So you see, now let's go to the symmetric group S3. Now we have permuted. Now the situation is worse because S3 contains 6 different permutations and only 3 of them are cyclic. C3 has 3 elements, and S3 has 6 elements. So it can be also generated with permutations. And again, the permutations can be given representations in complex plane. So which are the representations? Let us take first the Z3 group. We introduce J, the number, it's e to this cubic root of unity, and then we just declare that the permutation is 1. The first permutation, cyclic, will be given by J and another by J squared. By the way, we could have chosen the other way around. So one is turning in one way and another turning the other way around. Why not? You have 2 different representations. So these are the representations. You see, these are on the left, you have the Z3 group, which is just rotations. One rotation by 120. Next rotation, which is a square, is rotation by 240 degrees. And finally, the unit is when you come back to the power. And then I implemented the other three possibilities, the odd permutations. And the odd permutations can be generated by, for example, by complex conjugate. Then you start with black. You see there's a black point. And now the red points are the rotations. See, the first red point is the rotation by 120, and the second. But then you can start with complex conjugation. You get the green point, and then the rotations give you the green point again, the same. So we have the 6 points. The 6 points represent the result of action of 6 different elements of our S3 group on this one single complex number, which is the first one is a black star. So again, the odd permutations, here I give the definition, and of course we can give them some names. The complex conjugation is the bar, and then the other two are hat and star, okay? And then you have this combination. The whole thing can be generated by 2 elements. One is complex conjugation, another rotation by 100, and then you combine and you get everything. So here is the multiplication table.
And you just need to multiply. Right?
Yeah. That's complex number. Multiply the complex numbers, or act with this is conjugation. So you have, but conjugation, you have 3 different conjugations now. One is in the X, another is in the J, and the third one is in J squared. So this image of the 2 images of conjugation, which are obtained by the rotation.
These are basically the dihedral group.
Yeah. And then you have you can observe that only Z3 subgroup is abelian, because if you look at this sub matrix, they're symmetric, but the whole matrix, the entire matrix, is not symmetric anymore. It's non-abelian. So it's interesting. But to get grading, we need only Z3, the abelian, because the grades has to add up like numbers. So the grading is always given by an abelian subgroup. So let's see how it works.
Is it always the case that the grading is always done, right, by the abelian?
Yes, because the grades has to add up. No, otherwise you cannot add them up. You cannot add the complex number with some operation. So the grading is always like this. So again, now, due to this, you remember that we had 4 different classes of 2 forms. Now we have 3 different classes of 3 forms, because one is, of course, totally symmetric. These are the classes under Z3. One is totally symmetric. Another, you can call it J skew symmetric. And finally, J square skew symmetric. It's just the opposite. Yeah. So and that's all. That's all you can do with Z3. And of course, so the whole space of the 3 forms is the dimensions being respectively n cubed plus 2n over 3 for T, and n cubed minus n over 3 for S and S bar. And if you add up all this, you get, of course, n cubed. The whole thing is the total dimension of 3 forms is n cubed, of course, but they separate. Like, by the way, n cubed minus n is always divisible by 3. Is it obvious? Yes. because you factorize n, then for this left is n squared minus 1. But n squared minus 1 is n minus 1 by n plus 1. So you have three numbers, so one of them is always divisible by it. Yeah, that's true. So, n cubed minus n always divisible. But it's just very simple. Yeah. So, and then, of course, it can be anything, any free form can be a mapping into vector space, can be separated into three parts according to this symmetry properties. And of course, they are defined like this. This again is like symmetrization, anti-symmetrization. Here you have total symmetrization, J skew anti-symmetrization, and J square skew anti-symmetrization. And again, if you add up, of course, you see that if you add up all this, you'll get just W alpha ABC, because you remember, because always in these columns, 1 plus J square is always 0. 1 plus J square plus J is 0. So what is left is just the first column, 3 times, and that's it.
Can I ask something?
Yes, sure.
So, the total symmetrization, how should I think if I wanted to include all 6 permutations? And do, because in the set 2 grading, typically you have 6 terms and you just symmetrize.
Then we have to use V6 grading, because V6, because V2, now here we have only cyclic permutations.
This is only cyclic, right?
Yeah. Then we have to include non-cyclic. The non-cyclic will be generated by Z2.
Yes. And that will be done by conjugation.
Yeah, for example, whatever. You can choose anyone, because after they will generate the whole thing.
Or minus.
Yeah, whatever. But the problem is that Z2 cross Z3 is equal to Z6.
Yes.
This is not always true. The fact, if you take 2 cyclic groups and you take the product, it will give you the cyclic group of the product of these numbers only if they are relative prime numbers. For example, Z2 cross Z2 is not Z4.
Yes.
It's different. So you have to be cautious. But here Z2 cross Z3 is Z6. And of course, then you'll have, the whole thing will be much richer. It will be the same with minus sign. Then you have combined with minus sign or plus sign and so on.
Yes.
Yeah.
But this is the set 3 case structure.
Yeah, Z3 is just this. Or you go to Z6. Now, this is just a illustration, Z6, how Z6 works. You see that you have the minus J square can be identified with the generator of Z6, which is the rotation by 60 degrees. And then you get all these numbers. And of course, we can attribute colors, but that will work with Luba. It's different thing. And
that's great, because that effectively, it's creating some code of the coloring.
It goes even to quarks and color chromodynamics. It's very interesting.
Yeah.
Anyway, so this is just trivialities about Z6, Z2, Z3, and Z6, the 2 elements which are added, the Z2, and then finally you get the entire Z6. And of course, these are the of particular interest are the combinations that give you 0. And this is also interesting, that if you take the entire Z6 with 6 complex, Q is minus J squared, but Q is just e to the power 2 pi I over 6. So or it is just 60 degrees. This is the simplest rotation by 60 degrees, which engenders everything. It's a cyclic group. So we need only one. This is also interesting that here you need only one generator, which generates you the entire 6, but the 6 can be also seen as some of them can be identified with the S3 group, but they are not.
And obviously, this just maybe even for the audience, these relations generate or imply the relation 1 plus q squared plus q equals 0.
Yes, but
it's more than that.
Because you can find other combinations that give 0, and this is, of course, this goes to quantum chromodynamics, because you have 2 combinations. 0 means white.
Yes.
So you have 2 combinations that by 3. 2 combinations of 3 items that gives you 0, which is j plus j squared plus 1, or minus j squared minus 1. So you have either 2 combinations, which can be quark and anti-quark, and 3 combinations by 2. These are mesons. Then you have, these are nucleons, 3 quarks and 3 anti-quarks, or 3 components of a meson, pi plus, pi 0, pi minus. You see, you have 3 different combinations by 2. Q plus Q4, Q squared plus Q5.
And this is essentially the geometry of the hexagon.
Yes, of course. You can, by geometrically, you see, it's the same. If you look at the colors, 3 colors, blue, red, and green, give you white. But also magenta, cyan, and yellow also give you white. And also...
But also you can do magenta and yellow, and then, you can do...
Blue and yellow.
Blue and yellow, and then they also...
What do they give?
No,
this is
no.
0.
It is 0.
Yeah.
0.
Yeah.
Because yellow is red and green.
Yes, I'm sorry.
So if you add blue, again you have...
Yes.
So you have the same thing, you have this on TV screen.
Yeah.
But on TV screen you have blue, red, and green, because they are active. They're active. They are really emitting this. But if you take the paper and you want to print on it, what do you use? Not green. Why?
They are...
But you are subtracting, because you have white, and you have to subtract 1, and then you get... If you subtract, for example, if you subtract red, you get blue and green, which is cyan. And that's color algebra. That's exactly the same. So you have the color algebra, which is complementary colors on printer and real color. But why do we call it real? It's our eye. If our eyes were tuned into magenta, cyan, and yellow, which could be, then this will be used in TV screens, and the other ones because it's the same. You can add, or it's the same. So now we come to matrices. How to translate it into matrices? Because if you have 2 forms and 3 forms, again, maybe we'll have to add them up or multipliers. What can be done? So this is, we suppose that you have linear space. Well, that's the simplest thing we can imagine, linear space. And on this linear space, we have change of reference frame. Again, it's like it should be. And finally, these changes of reference frames have to form a group again, and now we go to, this is an important point, because what we looked before, what we saw before, were just forms. All these tensors had their indices down below. So these are called covariant indices because they repeat the indices of the frame. But then you have the contravariant indices. And you have somehow to, and whenever you have a linear operator, it must change covariant into contravariant because it contains both. So you must have also some kind of metric tensor. It can be metric or not, but some kind of irreducible and non-singular tensor that will enable you to put something, the index that was down, to upper position or to make a contraction. This is the sum, because I will say that summing up, for example, if you sum up just usually when you define matrix multiplication, you just write the sum A KL times BLM, and you sum over L with a sum sign. But this is this does not tell you how this will be seen under transformation. The real thing is to, if you sum up, that means that you have the symmetry somewhere. This is how we should read the, for example, if you have two matrices, that call them two forms, two forms. If you want to multiply them, that means that you summing the second index of the first one with the first index of the second one means that you have behind, you have the delta or metric or whatever how you call it, and that is how you, and then it's easy to see how to define a multiplication, ternary multiplication of three forms, again with this rule. And extending this rule means the first rule was reading the second index of the first one with the first index of the second one. So we maintain this, but now the second index of the first form will be with the first index of the second, the third index of the first with first index of the third, and the third index of the second with the second index of the third. And then what is left, again, you have only three. So this is correct, because now this makes sense in any reference frame. You know how they change. The matrices of transformation, they will transform, and under transformation, what was the product of three will remain the product of the same three. The transformed product will be the product of transformed things. This is guaranteed. This, yeah.
In the presence, but it's in the presence of a metric.
Yeah.
Yes.
But there's not only metric, for example. You can have in 3 dimensions, there's not only metric, but also, oh, I forgot. Anyway. In 3 dimensions, for example, you have a 3 form, a totally antisymmetric 3 form that is, in fact, it is the volume element. Mm-hmm. With this 3 form, again, you can first of all, you can ask yourself, I'll take 3 such 3 forms and I multiply them, produce a ternary. I'm sorry, this KP should be, well, sorry, I will correct it. And then you see that somehow this algebra is very simple. The ternary product of these epsilons, of these 3 forms, gives the same 3 form with minus sign. So produces.
You mean the second equation?
The second equation.
Mm-hmm. Yeah, if you apply the same rule.
The same rule as we take the rule with, here I put delta instead of G, just the simplest metric. So this is the result. But there's another. You see, if you want to get a 3 form out of 3 forms, so you have 9 indices. The 3 forms have 9 indices. So you have to somehow to saturate 6 indices instead and be left with 3. So here we saturate them 3 times 2, 2, and 2. We saturate it with delta. But there's another possibility to saturate with 2 times 3. I can put out 6 indices, either with 3 symmetric forms or with 2 anti-symmetric forms, with other epsilons.
Without epsilon?
The last line.
Yeah.
Again, if you saturate with 2 epsilons.
So the last one is second
IMP. Again, I want to leave the first index of the first one, the second index of the second one, and the third index of the, oh no, first index. Okay, somehow it's not, I think it should be, yeah, IMP, okay.
Yes, it's fine. It's the second, first.
I should have used
It's
epsilon RSP.
I think that,
this kind of even
I think the typo is in the first epsilon, right? In the right-hand side.
yeah.
It's in the first epsilon with the lower indices. That says epsilon ijk.
I thought it was in this.
No.
No, this one.
IMP. So everything should be saturated
Yeah,
except
so IMP
IMP.
is what remains.
Yeah.
That is correct. But
Yeah.
I think the jk after I in the third epsilon in the expression, that should be
No, K is saturated, N is saturated, S is saturated, J is saturated.
But how N is N is straight because of
No, everything is saturated.
I think maybe P and S need to be
Yeah, you can. No.
permitted.
Yes, if you want to have some logic in it.
Yes.
No, I agree.
It's correctly saturated. Yes.
No, the saturation is correct, but probably I made a typo because if I want to have a logic, I have probably to make a cyclic permutation, so to have some symmetry. Yeah, but anyway, if you compute it, it gives zero.
Gives zero.
Yeah, it's zero. It's nilpotent. So I don't know what it means, but apparently for this antisymmetric form, you have only one possibility of non-trivial ternary multiplication, which is with deltas, not with epsilon. But
Yeah, the epsilon tends to give zero.
Yeah.
When you put it in this.
no, it tends to give zero if it is applied to epsilons.
Yes.
But if it is anything,
No, of course.
Yeah, we don't know.
Of course. No, I mean the epsilon.
epsilon is nilpotent.
Yeah.
Absolutely.
Yeah.
So now another way to ternary structure is to generalize the Lie algebra, the commutator. So the commutator, as you know, it's just if you just take any associative algebra, you get xy minus yx, you call it commutator, and of course, by definition, it satisfies the Jacobi identity. By the way, there is a general definition of Lie algebra is just antisymmetric multiplication and Jacobi identity. And there is a very famous Hados theorem, which tells you that any such algebra, any Lie algebra, can be embedded into associative algebra, and then you'll have the commutator will replace the antisymmetric multiplication. But the price to pay is that this algebra, which is called enveloping algebra, its dimension is higher than the dimension of the Lie group.
Yes.
This is the price to pay. And we'll see that the same applies to ternary things. So, for example, we have what is the ternary generalization? It's, of course, again, instead of commutator, we will define ternary commutator. xyz plus jyzx plus j squared zxy. Of course, again, we could go further and define z6, but I have no time to expose all this. So this thing. By the way, it's also interesting that if the algebra is unital, this ternary commutators, they contain as a subset ordinary commutators. If you take the ternary commutator of x1 and I and y, one being the neutral element, not all the algebras have neutral elements, for example, the algebra has not.
So far, I'm just thinking of x and y being elements of an associative algebra.
Yeah, here it's associated.
Okay. But, okay, interesting. So if it's also unital, then it contains the actual
Yeah.
binary commutator. So-
Yeah.
Okay.
By definition, because j plus a squared is minus 1, and it is associated, and the 1 commutes with everything.
Mhm.
It's just that it contains all the algebras, but the price to pay is to introduce the neutral element.
Mhm.
So again, it's a way to see that it's not that exotic as one could think. It is exotic, of course, but if you can, there is a kind of pathway to ordinary, to familiar things. Although in this exotic algebra we couldn't find something like Jacobi identity. It didn't work. So
Sorry,
Yeah.
can we go back to that?
Yeah.
You said that you tried to search for a Jacobi identity
Yeah,
here,
yeah.
and you couldn't find it.
well, my student, with whom we worked, and with Victor, and that was in the late 90s, he found with 40 items.
Wow.
Yeah, which is better than 120,
Mhm.
but still it is, you see,
It was numerical. Once you found it.
symbolic. Symbolic. But 40 is,
What was 40 terms? What was it? What,
I don't remember.
but it was,
He was looking.
you found a combination that satisfied Jacobi.
Yeah. No, but here you have to take Jacobi's from 2 to 3. If you have a commutator between two things, you iterate it,
Iterate,
and then you
get
have 3. And the combination of these 3, because normally there are 6 different combinations. So the Jacobi and the 6 different combinations, if you take all permutations, there's 0, obviously, because there's anti-symmetry. So this is not interesting. So the Jacobi identity tells you that you don't need to have 6, which is trivial, but divide it by 2 and you get 3 combinations, cyclic.
Ah, okay, interesting.
This is,
For
Jacobi.
me, Jacobi identity means self-derivation.
Of course. But
But that you couldn't find in this, right?
no. Of course, it is behind.
Okay.
If you write the Jacobi, in a proper way, you see that it's derivation.
Yes, no. But the thing is that you say that you couldn't find
No.
that with this
No.
property.
So, but because it is, look how it works. If you have the ternary commutator,
Mhm.
then the next step is you have to add up 2 new elements.
Yes.
So you have 5.
Yeah.
Now, all permutations of 5 is 120. And of course, if you have the sum of
That's
this,
why you were saying better than 100.
the sum of this 120 obviously is 0, because you have this. If you make that's like with Jacobi. If you take the 6 ones, the symmetry of the skew symmetry gives you.
Yeah.
But 120, we know that 120 will give you 0, because you have always j with 1 with j squared, and they will eat each other.
Yes.
But this is trivial.
Yes.
But we hope that, so in some sense there is a logic. Jacobi identity reduce 6 to 3, dividing by 2. What our student found is dividing 120 by 3. 40. So there's the combination of 40 that is 0. You don't need to have 120.
So,
But it's still impractical. You cannot work with.
I'm trying to understand what exactly. So, this was found for any associative algebra over.
Yeah. For this kind of.
And
No, Jacobi identity just divided by 2. So instead of having the S3, you have Z3. Yeah. So here probably what he found was, I can't remember, because we couldn't even have it, even if you have it printed. You can't really understand. Well, if it is divided by 3, dividing by 3 means that instead of having Z5, S5, somehow.
but is it still true? Because the question to me is, does the commutator bracket, which is a ternary operation, does that satisfy the Jacobian entity exclusively? If you write the Jacobian entity, the ternary Jacobian entity, does it satisfy it?
You mean there's 40 things? No, the
It's one single equation for the bracket.
No. The ternary Jacobian, what would it mean? You have
It
to.
means that I might write on the
Write down.
in the blackboard after.
Well, okay, we'll discuss. Okay, good.
Yeah.
Okay, so again, I'm coming back to this. For example, we saw how it works, but I'm not forced to have epsilon in any. Suppose I have this free form. For example, we'll see that there is a free form in complex space of 3 dimensions. So it's possible. So anyway, one can produce. Now we have, you see, the combinations. Now we have simple combinatorics. Let us ask question whether we can produce a 3 form out of 3 2 forms.
Yes.
Possible. If you have another contravariant 3 form. So out of 3 2 forms, we produce a 3 form. Good. Now, what can we ask? Out of 2 2 forms, we can produce another 2 form. Good. Now, we can produce a 3 form out of 3 3 forms, ternary. If you have this one, see?
Yeah.
So what is missing? 2 2 forms give a 2 form. 3 2 forms give a 3 2 form. 3 forms give 1 3 form. What is missing? Again, 3 3 forms give another. There's another possibility. 3 3 forms give a 3 form, but with metric, symmetric tensor, or with something that is not, suppose, anti-symmetric. So you have 2 ternary multiplications of 3 forms. This corresponds in graphs. This corresponds to 2 possibilities of, you have 3 graphs, So you have 2 different possibilities to attach them and leave 3 free. One is in 2 dimensions, another you can not realize it in 2, but you can realize it in 3. Okay, so this is finally, again, is it possible to combine 2 and 3? Yeah, because 2 plus 3 gives you 5 different. If you subtract 3, you get a 2 form. If you subtract 2, you get a 3 form. So again, there's a possibility. So the full algebra is, so we have 2 products and 3 products. And of course, these things can be realized in graphically. But that is another topic. Now, I think...
We'll see that tomorrow.
No. I think I have to finish soon.
We started late.
Yeah, but still. So again, here's again the same thing. I'm repeating myself. So again, how we produce the matrices and again, I would like to say that the first idea that it is saturating second with the second index of the first one, with first index of the second, it can be extended to n. If you have n forms, you just produce, you'll keep the first index of the first form, the second of the second, and so forth. So you have the same logic. You can always produce an n-ary product of n forms with this idea, with, of course, with metric. Yeah, here it is. Yeah, here it is for 3. Again, with some. Although I prefer to use deltas.
Yes, but the deltas are missing.
Yeah. Here I'm just using the old-fashioned. Of course.
Oh, because I1 equals J1, I3 equals K1 plus.
Yeah. Again, you saturate it. It's just symbolic. Of course, you have to use deltas.
Yes.
But here it is better to see what is going on. The second one of the first with the first one of the second. The third one of the first with the first of the third. And the third one of the second with the second of the third. So this is the idea. And of course, you can extend it to any n forms and n.
This is the same product as before, right?
Yeah. But it's just written more clearly. So now, ternary, I'd just like to say that ternary, of course, any ternary, not any, but ternary algebra can be obtained by iteration. If you have multiplication by 2, you just iterate it and iterate, and then you have 3. But I would like to say that ternary structures are, of course, richer than binary ones, and there are ternary. It's easy to see that there are ternary structures that exist that cannot be made by iterating the simple product.
Yes.
But there's also a kind of Adolph's theorem that can be if you go to bigger algebra, associative algebra, you can always find matrices or something that will, but you'll have to pick up only some elements, and the rest is just for nothing because it's enveloping algebra. So you see that if we suppose that the ternary M3 product is just iteration of binary, I just put it on the basis elements. That's enough. Then the following, the structure constants, the binary structure constants have to satisfy it, but usually, except for some special symmetries, but usually the structure constants of the ternary algebra, you have n to the fourth, whereas the structure constants of the ordinary n to the third. So it's much, you have n to the fourth equations imposed, n to the fourth quadratic equations imposed on n to the n cube elements. So it's not always possible. Now, the next thing I wanted to show is when I started that we can use the Z3 grading to produce an algebra, which is generalization of Grassmann algebra. You see, you take 3 elements and say the cyclic permutation gives you J in front and another cyclic permutation, J squared, and then you come back and then you come back.
And so this product assumed to be binary or for the
Associative.
associated binary?
Associative binary,
Yeah.
It's associative. But you impose such things, and of course it cannot be realized as matrices.
Yeah.
Because if you take the trace does not depend on the order. So the trace will be equal to the trace multiplied by j, equal to the same trace multiplied by j. That one is there. Now the problem is that 0. The product of 2 matrices, of 3 matrices with 0 trace will not lead you to 0 trace. That's why. So, okay. So, of course, we can introduce naturally the conjugate algebra, which will turn like j squared instead of j, the other way around. And of course, it is, again, they are graded. We attribute grade 1 to theta's, grade 2 to the products, grade 3, which is 0, to cubic products. And of course, 4 products, they do not exist. It's very easy to prove. If the algebra is associative, then if you form a product of 4 such elements, then it's easy to prove. You just make 3 times to come back. But then you come back to this 4. This is because 3 and 4 are relative primes, so you cannot change 4 items with 3. It's worse than Rubik's Cube. It's just impossible. So you can never come back. Yeah. If you come back, you have J. So it's 0. So that's fine. So because this is very much simpler even than Grassmann algebra. Again, we already saw this, the symmetries.
Yeah, you're showing
the same thing. And cube minus n ternary products. And the same you have algebra, but there's something else should be added, because if you have 2 such algebras, one and the other one are ternary skew symmetric, but cubic skew symmetric, but how about the products? So these are binary. Let us see. You see, these are again all products you can produce with all these possibilities, all combinations. And this, of course, there will be 0. No, these are not 0 because they're conjugate ones.
Oh,
yeah, the conjugate, the 3. So you can go up to 6. 3 non-conjugate ones and 3 conjugate ones. But what is interesting, you see, that if you impose now on these binary products, you have to invent some commutation relations. So this is what we impose with minus sign. Theta A with theta bar is the same as minus j theta bar theta A, and then theta bar theta A is minus j squared. So you see that it is consistent. You make it twice, and okay. Why minus sign? This is again. This comes from quark algebra and from physics, because we want to. It's easy to see that if you produce the highest order, 3 theta A, theta B, theta C, and then theta bar, theta bar, theta bar, if you change the 3, then you get minus sign. You see, because whenever you change the order of theta with theta bar, you get minus j. Good. But then you have 6. So how many times you have to change order? You have 3 and 3 bars. Then you have to push one of the 3 non-barred through the 3. So you get 3 times, and then another 9 times. So you have to push 9 times in order to get the opposite order. And if you get 9 times minus j to power 9, j to power 9 is 1, so j to power 3 is 1. But minus 1 to power 9 is minus 1. So it behaves like fermions. This is the idea. 3 quarks and 3 antiquarks. If you change them, they're like fermions, like electron. Okay.
But it's, if you kind of accept, remember we discussed it, if you can have 2 possibilities, either the one where it's in agreement with Pauli principle, and the second one is when it's not.
Yeah.
So it's not the only possibility.
No. But here I choose this one because I want to produce fermions.
Because it's nice.
Yeah. Anyway, so I think, the last point is how the 3 forms naturally are appearing here. So you see, if you take a 3 form like this, it can be written because of the symmetry the same way. So this imposes symmetry on this 3 form. They are like this. By the way, it's also interesting that you see the thetas, when you made a permutation ABC to BCA, but with upper indices, we suppose that the there was a J. Now we have lower indices, and we see that it has to have J squared. This is, again, this is what is called the covariant and contravariant. If lower indices turn with some matrix, the upper indices turn with the opposite. But J squared is the opposite of J, because the product is 1. So this is why the symmetry is like this. And this, we produced a ternary multiplication and ternary algebra with these row matrices, which I skip because the 2 generators. If you have only 2 generators, it's very simple. You have only 2 combinations that are non-zero, 1, 2, 1, and then you have, of course, by cyclic permutation, you have 2, 1, 1, and 1, 1, 2, and or 2, 1, 2. These are the only possible. So we have 2 such 3 forms, which are J skew symmetric. And these 3 forms, we can ask ourselves, what is the product, the ternary product? So I'll just, this is the solution. I'll show you the ternary product of these 3 forms. Okay. Yeah, like this. You see, this is the ternary product of our 3 forms. And guess what it gives? Because alpha, beta, gamma, they are always 1 or 2.
Okay.
And this gives, again, the same for the... oh yeah, in order to get the required symmetry, we have to symmetrize this too, in order to make an algebra of. So we have to symmetrize it in order to get, again, the same kind of symmetry of indices. Now, once you get this, this is the algebra. 1 with 2 is 1. This cubic product gives -2, and 2, 1, 2 gives -1. And now the last thing, I will show you how the Ados theorem works, because these are not matrices, they are cubic forms.
Yes.
But we know that if we have an algebra big enough, this algebra is 2-dimensional. There are 2 generators. But we have Pauli matrices, and we can define now, this is like in Ados theorem. We define the skew 3 product just like we defined before in associative algebra. And then we see that we get the associative algebra is the algebra of Pauli matrices, which is 3-dimensional, not 2-dimensional. And inside we get 3 possible choices of realizing the other one. 2 and 1, or 1 and 3.
And is it why 2 choices?
No, because I chose tau 1 and tau 2. I need 1 with 3 or 2 with 3.
1 with 3, 2 with 3.
They will give the same thing. Yeah. You pick. The problem is to pick up 2 generations out of 3. So again, the enveloping algebra is bigger. When you pick up something, and it's of course it's possible that you have many choices. So this ternary algebra of 3 forms can be realized by associative algebra of matrices under condition that it is larger than, and it's probably the same with any. So I finished.
Yeah.
Sorry for being so long.
No, I mean, thank you so much.
Yeah. Thank you.
So let's maybe give it a couple of minutes, because I think there's another person who's coming.
Yeah.
And but if there are any questions from people here, I have a few myself. So
there were many questions during this. Hello. Nice to meet you.
So I think we can post it because we are actually following the lights from the. So we'll see. So if you have questions, I'll stop the
there was something else, of course. I made invariance, but that's.
But you finished already?
Yeah, no, I stop here because it's too much.
Yes, if there are some questions from the audience, maybe it's good time to take some questions, if there are any. I don't know if I don't see any in the chat immediately, so I have some questions and I can see it online. So generally, I was interested when you were mentioning this grading, right? The fact that you started and you were speaking about the Ternary algebras and the grading and the connection between those. So how did you put those together? That because of the fact that you have observed, right, some properties of these the general groups properties, or there were some other motivations behind?
No, the motivation was quantum chromodynamics, in which you have three colors, which add up to white combinations. What is observed are only white combinations of three colors, and there are three quarks with different colors that gives you a nucleon. So this, I always thought that there must be some algebra behind, and that was the motivation. And with my friend, first with Suzuki, then with Lukierski, and I published first myself, the generalization of Dirac equation. Dirac equation is based on Z2 cross Z2. There are two Z2 groups of invariance of Dirac. One is the spin up or spin down. The fundamental, the first observation by Pauli was that there is something to the electron that makes it two-valued function. It cannot be described by just one complex function like it is Schrödinger equation, that it has some degree of freedom which is dichotomic. It's two possibilities. And these two possibilities came just from Schrödinger equation. And because if you look for a hydrogen atom, then you discover that the state of an electron, if it is described by just Schrödinger equation and Coulomb potential and everything, then you get the solutions are Legendre polynomials of second kind with magnetic, with magnetic number and the principal L, the momentum, angular momentum. So then you discover that the number of states for a given energy is just n squared. This is what Schrödinger equation with one complex functions gives you. So the number of states should be 1 or 4 if you go to the energy. Second, third should give you 9 states. Fourth should give you 16 states, and so forth. But if you look at the periodic table, you discover that it's not 1, 4, 9. No, the elements go 1. Instead of 1, you get 2. Hydrogen and helium. Then the first level is finished. Then the second level, you get 8. From lithium to neon. 8. And then you get 18. So it is not n squared, but twice n squared. That Pauli understood that this 2 comes from that any state of electron must have 2 possibilities. So this was spin up, spin down. So this is one Z2. And then what Dirac discovered, so in order to describe it, you have to have 2 component function. But then Dirac found that the really Lorentz invariant equation should be realized in 4, not 2, but 4. But why 4? Because to his great surprise, he discovers that there's not only electron, but anti-electron. He thought first that it was proton, because you have particles with plus and minus. So there are two Z2. One is called charge conjugation, another is spin conjugation. But finally, Dirac didn't know that the positron could exist. So he thought that the positive was... yeah, but later on, they discovered the positron, but proton was not good because the mass is almost 2,000 times bigger, so it cannot be the same particle. So it's all fascinating how they thought about all these things.
Yeah. So I wonder if Victor, Andres, Olga have any questions or comments?
Oh, they know it by heart.
So maybe I will ask my so tomorrow actually, because you did mention that there's these possibilities of products that can be defined for three forms.
Yeah.
And with the presence of a two form and or a metric.
Yeah.
So tomorrow, just as a bit of advertisement and a question, my talk will basically present so we did an enumeration of all the possibilities, all the combinatorial possibilities that you can define this. And I think what is interesting, and my question is, how important do you think it is that you have a metric to define some of these products? Because some of them seem to just work fine with the delta canonical metric.
Yeah, delta is enough. I mean, because you can always, whenever you have a symmetric metric form, you can always find a reference frame. You can diagonalize it and you have delta. So it is enough to use delta, of course.
And because my point is, and we were going to talk about this, especially on the Wednesday, where we Josh will show about the Taylor-Messner product. So by the Taylor-Messner, actually, I think it was shown only a few weeks ago that it's equivalent to this product that you're introducing. The Kerner product.
No, it's so trivial.
It's trivial, I know, but so these things don't have names. So I call it the three-force product.
Yeah.
You know, video games, it looks like the diagram looks like this Zelda video game symbol. But anyway, the conjunction pattern is indeed one index in each of the forms is free, and the other two are contracted. Right? So you can change that combinatorics, and you can, for example, have two indices of the same three form are free, and one index is contracted. So if you do that, then obviously the two indices have to be binary. They are repeated but not summed. It's strange, but it gives you a well-defined array multiplication. But the problem, of course, is how to define it in terms of a matrix multiplication or a tensor.
Or tensor, because if you don't know how it transforms, usually it's
you don't know what it is. Exactly. So I think that we have a lot of evidence that there is something there. But it seems that covariant contravariant multilinear algebra is insufficient to bring it out. Because it seems that it's something that you can clearly define, just write it down. And you can see the contraction with the pairwise contraction with the triple delta. So the diagonal. Yes. So you shift the burden to understanding the triple delta. And so have you thought about the triple delta?
Not triple delta, no. There is something like triple thing with this skew product. I encountered it when we generalized, this is called nonions, the generalization of Clifford algebra. Then you have, it is another story. I didn't tell it here. Then you have cubic, again, Q1, Q2, Q3, the matrices, 3 by 3 matrices. You make and then you get the structure constants. The structure constants are ternary. So you get something that looks like this triple delta, but it takes values not only in numbers 1 or j or j squared. So, but it might be different interesting because not only 1 or minus 1 or plus or 0, but you can have also 1 j and j squared. Look at this, how it's, I don't know, because your matrices are complex too, or not?
They can be.
Can be,
Yeah,
yeah.
they can be. Yeah, they can be. But we only need to film semi-group.
Yeah.
So, yeah. So, by the way, I hope you can hear me from the call. I think it was fine until now. We are going to have a longer break, so we will resume at the original time, which I think was 4. Okay, so actually only 25 minutes. It's not long. It's nice. So yes, we will resume at 4. We are going to stay here in the room. We're going to discuss on the blackboard, get some tea or coffee or whatever. But and then we will be back for Viktor's presentation.
Is it okay for you, Victor? We hear us?
Victor?
Well, I guess yes. I see that Olga is connected as well. That's great.
Where's Olga?
Olga is the...
Yeah, but I can't see her. So.
No, she is connected.
Just connected to the camera.
That's great. I hope that is fine. And we will all connect.
James, can you hear us? Just to make sure that we are not talking to the board.
No. Yeah.
Yes.
Yeah. Perfect.
Okay, great. So yes, we will resume at the top of the hour, wherever you are, your attention. Thanks very much. And thanks, Richard.
Thank you.
Thank you.
We can
We're good to resume. Perfect. Welcome back, everyone. Apologies for the delay. We had, as I mentioned earlier, one of our speakers unfortunately had a family emergency and they couldn't be here. So maybe he will be able to present later on during the workshop, but for now we would have to move this talk. For now, we're going to continue with the program with Viktor Abramov. He's going to talk about Biunits in Ternary algebras of hypermatrices. Viktor, the floor is yours.
Yes, thank you for introduction, and thank you for invitation to give these online talks. So should I make it more larger, this picture of my screen? Or it's okay?
It's okay. You can also go full screen, but it's okay. We can see it fine.
Okay. So in this talk, I will consider structures which are very similar to the ones which were considered by Richard in his talk. And so the first structure which I'm interested in is a ternary algebra of hypermatrices. So by a hypermatrix, so you understand, I mean an nth order hypermatrix. So it's a complex valued variable with three subscripts. It's denoted T and subscripts I, J, K. So where K, where I, J, K, they're integers and they run from 1 to n. So for this kind of objects, we have several names. And so we have no firmly established terminology in this field. So the same are called cubic matrices, three-dimensional matrices, spatial matrices, and even three-index matrices. So I will use the term hypermatrices. Hypermatrices, and so I will consider the hypermatrices of the order 3. So, and of course, this hypermatrices is very interesting objects because they so to speak, provide a natural building material for ternary products. So I will assume that that hypermatrix is defined on a Euclidean space, and so in this case I have no difference between covariant and contravariant indices, and so I will use only covariant, I mean subscripts. So, and in this case, when I change a coordinate system in Euclidean space, so I will consider this hypermatrix as a SO3 tensor. So it will transform under the action of the rotation group. So the Euclidean space will be three-dimensional. So all subscripts runs from 1 to 3, and this I will call the third-order hypermatrix, or simply hypermatrix. But I will also assume that it's a tensor. So when I have a change of coordinates, it transforms according to the by the rotation group, and this is shown on the next slide. So of course, here we have an addition and multiplication by complex numbers. So we have a structure of the vector space, and this vector space is 27-dimensional. And now the action of the rotation group on this vector space of hypermatrices is defined by this. So here these two are hypermatrices, and the G is an orthogonal matrix with determinant equal to 1. So I will use, but this of course natural, Richard used this Einstein convention that repeated indices, we mean summation over the repeated indices here. So we have a summation over I, J, and K. So, so yeah, we can, so I can say that this formula defines an action of rotation group on the space of hypermatrices. So or the hypermatrices. Or I can look at it from the point of view of representational theory. Then I can say that I have a tensor representation of the rotation group. So if I take an element of the rotation group, put it here, then I have a linear transformation in this 27-dimensional vector space of hypermatrices. And so from this point of view, from representation theory, so what we know about this representation, tensor representation? So actually we know that the whole space can be decomposed into the direct sum of 4 subspaces. They're written here, and the subscript here means the weight of representation. So we have it's very important that this decomposition is unique. So we can uniquely decompose into the direct sum of these subspaces, and in each subspace we have a representation of the rotation group which is multiple of irreducible one. So in each subspace we have a several times repeated irreducible representation, and the general method to get this irreducible representation, we have to split each subspace into direct sum of subspaces, of course in a way which is invariant under the action of rotation group, and then in each subspace we will have an irreducible representation. For example, the first subspace is a zero-weight subspace. Here we have only one-dimensional representation, and this subspace is of totally antisymmetric or skew-symmetric tensors, which is written here because this epsilon, of course, this is not epsilon, this is the same as Richard used in his talk. This is a Levi-Civita symbol, so totally antisymmetric tensor. And this is one-dimensional space, and we have one irreducible representation. Next, one-weight representation. This is a space of third order, of course, hypermatrices or third order tensors of this type. And here we have 3 times repeated irreducible representation. And of course, we can split this subspace, this subspace into 3 ones according to this, like this, and then we have an irreducible representation. So I'm most interested in the weight 2 representation space, this one. Why? Because first, in this subspace, we have twofold irreducible representation of rotation group. So this space is 10-dimensional, it's written here, complex dimension. Complex dimension is 10. So if we split it into the direct sum of 2 subspaces, then there will be 5-dimensional subspaces, and in each subspace we will have an irreducible representation of the rotation group. So this space will be most interesting for me. And the third one is a subspace of totally symmetric tensors. This is a 7-dimensional, and here we have only one irreducible representation, so no need to split it into subspaces. It's an irreducible representation of the rotation group. So now about this space. So what we see here, we see that, how can I say by words describe this space? This is traceless hypermatrices. So traceless means that the trace over any pair of subscripts is equal 0. So the first one here, I take a trace over first 2 indices, subscripts, 0, first and the third one, and here second and third. So about this, I will say that this is a traceless hypermatrix. So the traces over any pair of indexes is 0. And now here you see that we have one more condition, and here we have a cyclic permutations of subscripts, and the sum of the values under the cyclic permutations should be 0. So, what is the motivation? Okay. So, and now I will show. Now I will study this subspace of hypermatrices. And
can I ask a
yes.
question?
Yeah, please.
Can you go back to the previous slide for a moment? So why? I guess that you can also have a SO3 cross SO3 cross SO3 action, right? On tensors. You could have it, right?
Oh, yes, you mean SO3 times SO3 times SO3.
Yes.
Yes, I can say this, yes.
Okay. So, but now we are just looking at sort of the diagonal action of that, right?
So I transform each subscript
With the same.
ijk with these matrices.
Yes. So it's always the same matrix. It's some kind of cubic diagonal action.
Yes. G is the same. Yeah, G is the same.
Okay. Yes. Just clarifying. Yes. Thanks.
And related to that, so reason why you wanted to consider that, because you said that you used some kind of motivation from what? Yeah, because I was missing a bit of the motivation on the back, of the interest specifically in that. But I guess it's already interesting itself to consider that.
Yeah. But motivation will be later.
Yeah. Okay.
Usually I start with the motivation, but now I decided to start not from motivation, but first from the algebraic structure, and then to explain what kind of motivation will be here. So here we have a tensor representation for the rotation group. Now uniquely can be split into these subspaces. And now here I will have a twice repeated irreducible representation of SO3. And if I want to distinguish with irreducible representations, then I have to split this subspace in turn into two 5-dimensional subspaces. How can I do this? This is not unique. So here we have several possibilities. But I think the most natural one that we solve this equation, and here we use a primitive third-order root of unity. So now, Richard denoted this third-order root of unity by J. I denoted it by Q here. So you should keep in mind that in Richard talk, this was denoted by J, but I don't know, I used to denote it by Q. So here we have properties of this parameter. So the sum 0, and if I take a complex conjugate, then I get this Q squared. So, and this is a general fact that any hypermatrix can be represented, can be decomposed into the sum of 3 components. Actually, Richard used in his talk this decomposition. So I can write here sum of cyclic permutations without Q. Here's the sum of cyclic permutations multiplied by conjugate Q conjugate Q, and vice versa by Q and Q conjugate. So now if I took the sum of these components, these 3 give me T, I, J, K, this, and this 0, this, and this 0. So I get T, I, J, K, so it's some kind of identity. So, but now if I restrict this decomposition into this subspace, then due to this condition, the cyclic sum is equal to 0. I get that the first component is 0. And so now if I restrict this decomposition, so by other words, I assume that this hypermatrix belongs to this subspace. Then I have only 2 components, this one and this one. So, and they are denoted here prime and two primes. So, but if I study the properties of these components, then the first components, I mean the property under the cyclic permutation of subscripts. So if I perform a cyclic permutation of subscripts for this component, then it's easy to find that it transforms like this. By other words, if I perform a cyclic permutation, then the right-hand side will multiply it by Q conjugate. In the case of the second component, if I perform this cyclic permutation, then it will be multiplied by Q. So Richard showed the same kind of variables in his talk, but in this context. In this context, why I use this decomposition? Because I wish to decompose this space into two 5-dimensional subspaces. And this formula shows that I can do this by taking these components or projecting this hypermatrix first to this subspace and then to this subspace. So actually this formula shows that I have a decomposition into two subspaces. And these subspaces can be defined as follows here. They're written here. So, but this is important here that I also have this traceless condition. So first, I have hypermatrices which transform under the cyclic permutations with the Q bar or Q. But I have an additional conditions that the trace over any pair of indices is equal to 0. So so we have no firmly established terminology in this field, and Richard called this J skew symmetric term, and I call this Q cyclic hypermatrix. So Q cyclic hypermatrix means, in my talk, means that first it transforms under the cyclic permutation with the Q, and of course, this hypermatrix should be traceless by any pair of indices. So now the direct sum of these two subspaces gives me this subspace. And in each subspace, in this one and in this one, I have an irreducible representation of SL3. Now motivation is here. The motivation for this is a Ternary generalization of the Pauli exclusion principle, which was proposed by Richard. So his reasoning comes from the model of quarks. So we know that quarks are most fundamental particles of matter currently known, and all hadrons are composite particles made of quarks. And Richard mentioned in his talk that fermionic baryon is a combination of 3 quarks, and the meson with integer spin is a pair quark-antiquark. So, and we have 3 generations of quarks, and in each generation we have 3 flavors, which are denoted, up, down, charm, strange, top, bottom. And of course, all combination of quarks should be colorless. And in quantum chromodynamics, quarks are treated as fermions with half-integer spin. And in this sense, they obey the classical Pauli exclusion principle. But according to quantum chromodynamics, in a stable bound state, there is place for 2 quarks in the same U state. For example, proton is a UUD or D state, 2 D states, neutron is a combination UDD. So, and the Richard proposed generalization, which he called Ternary generalization of Pauli exclusion principle. No three quarks within identically equal quantum characteristics can form a stable configuration that is perceived as a strongly interacting particle. Of course, I'm not a physicist. I'm a mathematician, and I know that physicists sometimes say that there are some excited states of which leave a very short time particles which admit the three equal flavors. But if we assume that this is stable configuration, then this Ternary generalization of the Pauli exclusion principle will be okay. So, but algebraically, what does it mean that no three quarks can be in the same identical quantum state? So, for example, if we have a wave function of a quantum system of three particles, and we denote the quantum states of this particle like this, and the value of the wave function on these states we denote by this. So it's very, we can see here an analogy with the hypermatrix. So then, according to this Ternary generalization of Pauli exclusion principle, when these subscripts are equal, then the wave function should vanish. And now, if we take a superposition of this of three states, then for this superposition we will have the same. So if we put here this superposition state, the value of the wave function should be 0. But now, if we take into account that this wave function is linear, then we find that the wave function should satisfy this condition, where we have all possible permutations of subscripts. And now we have several cases how we can solve this condition. First one, when we assume that this wave function is totally antisymmetric, and this will be consistent with the Pauli exclusion principle of Fermi-Dirac statistics. So, and from algebraic point of view, the algebraic structure which is adequate to describe this situation is a Grassmann algebra. Now, for me, it's very important that here we see that the wave function will be traceless. So if we take the trace over any pair of indices, it will be 0. Of course, it seems a bit strange because, of course, it's natural when we assume a totally skew symmetry. Of course, it's natural that, and people usually do not pay attention to this. But for me, it's important that the trace over any pair of indices is equal to 0. So now we can solve this condition in another way. We can assume that the sum of cyclic permutations, this part of the left-hand side of this equality equals 0. Then, of course, this will be also 0. So, and now you can see where the motivation comes from. So here, now I will show the representation theory. So here we have a hypermatrix which satisfies this condition. In this condition. And now, of course, we can solve this equation by assuming that the wave function has this property or this property. And you can see that by this, from representation theory, by this, we split this space into two subspaces where we have an irreducible representation of SL3. But I would like to draw your attention that that in my construction, I always assume this additional condition that the trace over any pair of indices is equal to 0. At the first glance, it seems it seems technically. No, of course. First reason why I require that the trace is zero over any pair of indices is representational theory, because in this case I can put it into the frame of representational theory and to get an irreducible representation of SO3. But when I think about this, it seems to me more and more natural, because if I do not assume that the trace of any pair they are traceless, then I go very far from this, I would say, classical case, Fermi-Dirac statistics or Pauli exclusion principle, or from Grassmann algebra. But if I require this, that the hypermatrix should be traceless, then I would say, then I can put all these cases on the same roof. So they're not very far from. So they maybe, of course, it's not a rigorous explanation, but they are more closer to each other. I do not go very far from this classical case. So now about this hypermatrix. So this is technical. So I put the entries of this hypermatrix like this. So here I have by blue color, I have an entries with the first index subscript 1. Then the second black with a first subscript 2, and the third red one with the first subscript 3. And the other indices, second and third, they the same as enumeration of entries in the square matrix. 1, 1, 1, 2, 1, 3. So now it's easy to see that in hypermatrix, if I put it into the space, I have 3 directions, and I call them.
Can we briefly interrupt and ask? So the link here would mean the transformation, the relation between the T1 matrix, right? Hypermatrix, sorry. How you can...
What kind of relation?
No, okay.
So this is more closer to us. This is in the middle, and this is far from us. I put these entries, replace these entries in the 3-dimensional space like this. Okay, it's not very important, because it's maybe important for me because I imagine this hypermatrix. Its entries in the space like this. So now I have a structure here. So I have 3 directions. So because I usually denote these entries, I will go back a bit. But I will denote it I, J, and K. I is the first, J is the second, and K is the third subscript. So I call this direction is I direction, because here I have an increase of the first subscript, 1, 2, 3. Then this direction I call J direction, because here I have an increase of a second subscript, 1, 2, 3, and the third one is this one. This is the K direction, because now then the third subscript increases by 1 here and 3. So, and actually I can cut this cube by planes which are perpendicular to the corresponding directions. If I cut by planes perpendicular to the ith direction, I have these square matrices. When I cut by planes perpendicular to the j direction, then I have these matrices, and so on, and so on. These matrices, they are square matrices 3 by 3, and they are very useful in what follows. So here I show these directions, how I split this cubic matrix into square matrices. So how I will denote them? I will denote them like this. For example, if I fix the first subscript, well, then I will show here by this superscript. So this shows that the first subscript is fixed, and the value of this fixed subscript is 1. So I get this matrix. Here I fix the first subscript, but the value of the first subscript is 2. Then I get this black, and the red one is this. I fix first and give it value 3. So now I split it into the matrices, and I will use these matrices later. So now, but I can also represent all information, all entries of this hypermatrix by taking these square matrices and writing them from the left to the right. So the blue one will be this, then this black one, and this. So here I have all entries of this hypermatrix. So now in this talk I will be interested in algebraic structure based on a ternary multiplication. And so you know that an algebraic structure called a semi-heap, which is a set equipped with a ternary multiplication, which is denoted by dot, and which satisfies the generalized associativity. If I have 5 elements, then this ternary product satisfies this generalized associativity. So this is also called, I used to call it a second order associativity, but I see that that in paper I will show it. In the paper written by Carlos and his collaborators, heaps of fish, they called this generalized associativity. So I decided to call it in this talk also generalized associativity. So when H is a vector space, then the whole structure is called a ternary algebra. So this is a very good because by ternary algebra, different authors means different structures, various structures. And I like this terminology. So vector space and ternary multiplication, generalized associativity, which is a ternary algebra. I think this is a very good terminology. So I mentioned this paper. It's the date of this paper is written here. So there you can find an excellent overview of the theory of semi-heaps. I would say that I knew not very much about semi-heap and heap theory, and for me it was very interesting that Soviet mathematician Wagner developed this semi-heap and heap theory, and his motivation came from differential geometry, where we have a smooth manifold and atlas of a smooth manifold, which consists of local maps and transition functions. For me, it was very interesting. And now I will also use the same terminology proposed in this paper. So the neutral element for ternary multiplication. So we have a by unit, right or left. For right by unit, we have this condition. So here, right by unit is denoted by E. A is an arbitrary element of a semi-heap. If we multiply it from the right and get the same, we call this a right by unity, or it's called a right by unity. And for left by unity, we have this condition. So, and if E is a right as well as left, It's called a biunit. And the heap is a structure where any element is a biunit. So we have this for any A and B. And of course, it's understandable that in the case of the transition functions, we have this. So now I will remind you a theorem. We proposed this theorem in the paper, which is date of this paper is written here. It appeared in 2009. So in this paper we have several things, but one of them is the associative triple products. So we prove the theorem that if A, B, C, and so the complex hypermatrices, then we have only 4 different triple products which obey the generalized associativity. It's interesting that generalized associativity, and these products are written here. So, and if here we have a diagrams which shows how we take a summation over the subscripts. So here first and in the first, last in the first, last in the second, and in diagram we simply connect them by corresponding lines. And so if we look at this, then we see that these two are very similar to these two, and some kind of similarity. I agree that we have some kind of similarity here, but these two products, triple products, are different. So, and I remember that my doctoral student, Sergei Shvitov, I posed him a question. He was from computer science, but he was interested in mathematics, and I posed him a question that can we find all triple products of hypermatrices, which obey either associativity of the first kind. This is simple associativity. You have 5 elements, and you group them by brackets. First on the left, then you shift brackets to the middle, and then you shift the brackets to the right, and all this should be equal. And it turned out that there are no such ternary products which could obey this first kind of associativity. But we found 4 products which obey the second kind of the associativity, which is called here in this talk generalized associativity. I would say honestly, I forgot about this result. But when I saw this paper, Heaps of Fish, it reminded me of this, and I decided my idea was to apply this, to study these products in the case of the Q-cyclic traceless hypermatrices. Why? I will explain on the next slide. Okay, it's for me it was really interesting. First of all, when I read the paper Heaps of Fish, I couldn't understand what is a fish product, but fish product. But then I understood that if you depict this diagram, so these triangles, and you put this marked by red, where you take summations, and it actually resembles the silhouette of a fish. So, but I will consider not a fish product. Fish product is the last one. I will consider the previous one here in this talk. I will consider this ternary product. And to distinguish between them, I will denote, maybe it's not very important. So I will consider this product. This is a fish product, but I will consider this one. So why? Because I was interested in SO3 invariants of hypermatrices. So as you see, I have a tensor representation. So I will say that I have a connection of an SO3, as Carlos says, SO3 times SO3 times SO3. And it's very interesting what kind of invariance I have here. So what kind of invariance of a hypermatrix? So first one is a linear. Here we have a complete table of linear and square and quadratic invariants. Linear invariant is only one, this one. But in the case of the Q cyclic traceless hypermatrix, it doesn't give anything, it vanishes, because this equals 0 and this equals 0. So now the table of quadratic invariants. So here you can see that starting, this is complete table of quadratic invariants, and starting from 8, I have only zeros, because in each product I have a trace. For example, here I have JJ, 0, KK, no, okay, it's from this starting from 0. Only these 5 could be non-trivial, I'm sorry, 7, maybe non-trivial invariants. And now if I look at these invariants, then I see here, for example, this invariant. I take JK, and this is very similar to this product. So here I have this part of the ternary product. So I calculated this invariance of the case of the Q cyclic traceless hypermatrices, and I found that there are only 2 non-trivial invariants, this one and this one. All other either zeros or they can be expressed from these 2. And if we look at this invariant, then it's not very hard to see that actually this defines a Hermitian metric on the space of hypermatrices. Why? Because look, here we take ijk, we multiply each entry of the hypermatrix with the same entry. So we interpret them, let's say, as a complex vector in the space, and here we have a complex conjugate. So actually, this is a Hermitian product, and it's not very surprised that we can define now the Hermitian product, Hermitian metric on this space, and we define it like this. Of course, this is invariant under the action of the rotation group. And the second invariant is this one. And my idea was that this invariant can be obtained from this ternary product, from this one. Now, I calculated both. So first of all, now we have a Hermitian metric on the whole space of third order hypermatrices. But I'm interested not on the whole space, but only on the space of Q cyclic traceless hypermatrices, which is 5-dimensional. And so this Hermitian matrix gives me a possibility to find an orthonormal basis. And I found it. This orthonormal basis consists of 5 hypermatrices. This. I will say one more time that I consider the space of Q cyclic traceless hypermatrices. So trace over any pair of indices is 0, and they satisfy this transformation rule that cyclic permutation multiplies by Q. So this is a 3 and 2 more hypermatrices, this one. So, and this basis is orthonormal. So if I calculate the Hermitian product of these matrices, this is Kronecker delta. And now I can identify any point of 5-dimensional complex vector space with a hypermatrix. So now I have an identification, or by other words, I parameterize 5-dimensional space of Q-cyclic hypermatrices by these 5 parameters. I call them coordinates. So now I have an identification, and for me it's very interesting because motivation comes from Ternary generalization of Pauli exclusion principle, which potentially holds in a quark model. And now I have a very interesting geometric space, five-dimensional complex space. Each point of this is a hypermatrix, some kind of cube, some kind of have a cube structure. So, and I think maybe this is an adequate geometry for the quark model. So now, but what about this ternary product? So I decided to find this ternary product, this one, not this product, but this one. In the case of a Q cyclic traceless hypermatrices. And when I started calculations, I found that this kind of matrices have a nice property, so which is written here. So if I cut, as I explained before, if I cut them by planes perpendicular to one of the directions, then I have three square total matrices. For example, I take case direction, then which means that I fix the third subscript and put it value p. Then the corresponding here, I have three matrices here. They are written here. So, and they satisfy the very nice relations. So if I take a product with the same subscripts here, then the trace of this product is this bilinear form. I will explain what this form is, because this form is, for me, is very important. And if these subscripts are different, then I multiply like this: u, v, vu, I interchange the order, I interchange them. Then it turns out that this is a traceless matrix. If I calculate the trace of this matrix, it's 0. Why it's important, I will show later. Now, what is a k here? K here. Now, if I calculate the invariants, two independent invariants, the first one gives me a Hermitian metric. This is a canonical Hermitian metric calculated now in coordinates of this five-dimensional space. But the second one is this bilinear form, and here is the matrix of this bilinear form. And I was very interested for this invariant. Geometric meaning is very understandable. This is Hermitian metric, but what this kind of invariant gives, so I can interpret this in different sense. I can look at this as a tensor. As a tensor is a five-dimensional complex vector space where I have a unitary transformations, because I have a Hermitian metric and I can reduce the whole group of non-degenerate transformations to unitary transformations. It transforms like this, and I studied the property of this invariant, and we wrote a paper, published a paper. So here in this paper, we studied the geometric meaning of this invariant. First of all, it's symmetric, it's unitary, and these properties are invariant under the unitary transformations. Determinant is epsilon. By epsilon, I denoted here the 6 for the root of unity. And of course, it also has some additional properties, but these not unitary invariant, they are real unitary invariant. So if we take the 6th power of this matrix, it's an unit matrix, and eigenvalues also invariant here. And so we studied the geometry of a complex dimensional Hermitian manifold with additional structure determined by this invariant. So on each tangent space of this manifold, we have this invariant. And for example, an example of such a manifold is as U6 factorized by U5, but it's not directly related to the material of this talk. Maybe I will continue now. So here Here I multiplied and I get this bilinear form. And now it's useful to introduce the notion that hypermatrix.
Yes, Richard has a question. Let me bring the microphone closer to him.
No, are the 6 matrices which are traceless? Can you express them as Gelman matrices, 3 by 3?
Richard, you mean these matrices?
Yeah. You have 6 traceless matrices, yeah?
Mm-hmm.
Gelman matrices are also 6 traceless matrices. No, 8, sorry.
8, because dimension of SO3 is 8.
Oh, yeah, 8. So maybe it's a subset.
It's an interesting question.
This is probably without Cartan subalgebra.
Maybe, yeah.
Yeah, I think, yeah.
Yeah.
There are the 6 ones which are not commutative.
So I have to think about this. It's very interesting.
Okay, thank you.
Maybe here will be a relation with SO3. Maybe.
Yeah,
Maybe.
must be. Yeah. Thank you. Sorry.
Now, so I call the hypermatrix I to regular if the second invariant is non-zero. So it can be calculated like this, or if I wish to calculate it, so I have an identification. Each hypermatrix is parameterized by these 5 coordinates. I can calculate it in coordinates. In coordinates, of course, it's in coordinates. It's this. It's the same, it's equivalent. So if this second I to invariant is non-zero, then I call it regular. Why? Because now I look at the ternary triple product, which is different from the fish product. So now I'm interested in this part of this product. Now I see that I can write it, I can put it into this way. Here I fix P, this is a third subscript. Here I fix K, this is also a third. So I have 2 square matrices, and before and earlier I denoted it like this. Then you can see that I multiply as these matrices and take the trace R. So now the triple product can be written if I introduce an auxiliary third square matrix H. It's introduced like this. So I multiply these sections, square matrices, and then take a trace. And now the whole triple products can be written here at the right-hand side. So I have this H auxiliary matrix. But now I remind you that these matrices have a nice property, which I showed before. Oh, I'm sorry, I missed this. Yeah, here, this property. So when this subscripts equal, I have this bilinear form. But when they're different, then and I interchange them, then I have a traceless matrix. So which gives me the following result. If now I interchange this here, U and V, so I will have minus here, because this is a trace. And the trace of the sum is 0, so which means that if I interchange U and V, then I have minus here. And this shows me that this triple product is antisymmetric, skew-symmetric with respect to U and V. But what does it mean? It means that if I put equal U and V, then the non-diagonal part will disappear, it will vanish because of skew-symmetry. But when they are equal, I will remain only with the diagonal part, which is this bilinear form. But what does it mean? It means that if they are equal, and then here I will have a delta, and which means that I simply multiply this t by this bilinear form, which is very similar to neutral element, to the right biunit. So, and now it's really so. Now I calculated all this. So the diagonal entries of H equal to this invariant, but non-diagonal part. Of course, I said that from this property, it follows that it should be skew-symmetric. We can see it here that it's skew-symmetric with respect to u and v. Here we have these coordinates. And also it's skew-symmetric with respect to p and k. And so here, in order to put this general formula, I introduced this some kind of analog of Levi-Civita symbol, but this is some kind of Q analog of this Levi-Civita symbol. I needed simply to write this formula because I have 3 different matrices, and to put it by single formula, I have to use some kind of this Q analog of Levi-Civita symbol. So now, for me, it was very interesting that this is, so when I looked at this, I didn't see immediately that actually this is a bivector. So I have 2 5-dimensional vectors, and the second order determinants composed of their coordinates. This kind of object is called bivector. And bivectors is closely related to Clifford algebras, but today I'm not able to explain why bivectors appear here. So now we can prove a theorem. So if U is a third order traceless Q-cyclic and I to regular hypermatrix, then this hypermatrix will be a right biunit of the ternary algebra of third order hypermatrices, which means that if I multiply, this is not fish product, multiply from the right, then it will be the same. So for me, it was very interesting that in this ternary algebra of hypermatrices, we have a family of right biunits, and even they form the whole subspace of Q-cyclic traceless hypermatrices. So that's all. I don't know how about the time.
We are around at the hour mark, but we have 5 minutes and some questions as people would like to continue.
I missed the notation actually that you used where you introduced. Can you please go to the I2 regular matrices?
This one.
Yes, thank you. Okay.
So I have a question actually on this slide. You say that this product is or is not the fish product?
This is not a fish product.
And
this is the second.
Because it has a twist in the indices, right?
Yes, this is the second one. So I twist here these indices, not the same order. I twist them.
Yes, I see. So, okay, maybe let's get to the end and then I'll ask my question at the end because I want to, because that theorem seems very somehow expected in a sense in this context because of the shape of the fish product up to symmetry of the matrices involved. So that might be the. So maybe I missed it because I had to take a call briefly. But did you relate this product to some concatenation of binary products and a transpose?
Yes.
Okay.
Yes, and the fish product in this construction, the fish product is closely related to the Hermitian metric.
Yeah.
Because in the fish product we have the same order. When we multiply, so we have.
Yes.
Here we have the same order RS and RS.
Yes.
And this is very similar to this invariant, which is a Hermitian metric. And so I think that the fish product will generate the Hermitian metric on this subspace.
Okay. Yeah. But what I mean is you can express, if you take the hypermatrices, you take as matrices with a multi-index. So you look at the first two indices as a multi-index and the third index as a single index. So you can regard them as ordinary matrices, but just grouping the indices. Then the expression of the product looks like, in the fish case, it looks like A times B transpose times C. Or
Yes.
But the other one obviously is twisted from that, so it doesn't look like that. But under some symmetry conditions of the matrix involved, we will have some behavior like.
Yes. If I assume this q-cyclic behavior of this matrices under the cyclic permutation, then of course I can transform this from one.
I see. So that's how I understand that theorem. It's correct to think that it's essentially that I am doing U hat transpose times U hat, and U is essentially unitary in that sense. When you go to your theorem in the further slides, right? There in the formula. So this idea of a biunit, especially a right by unit.
Right by unit, yeah.
Yes, right by unit. If this weren't, so if I just take the fish product, not this one, but the fish product,
yes,
then a right by unit is equivalent to once you express with multi-indices to a unitary matrix, basically some kind of unitary property where you have U times U transpose equal identity, right? So I guess this is weaker than that, but it's a similar sort of situation, I imagine.
You mean some transposition here?
Yes, I mean that exactly. So, well, it would be in the middle one, but
this way.
Yeah. Same idea, because the fish product will literally be a transposition of if you group multi-indices in 2 and 1 and 2 and 1 and 2 and 1. In this case, there's a twist, so it won't be the case explicitly and literally, but up to some symmetry of the matrices involved, it might be the case. And so I wonder if this theorem, this result, can be interpreted as these are the conditions that you require to define a transpose for a particular subclass of matrices, which they're a bit more general than unitary because they need not be square, for example, right? So, but they do satisfy this condition of unitarity, that matrix times transpose equal identity, right? So maybe that's a way to rephrase this result. I'm just wondering.
Yeah, and also.
Maybe yes.
Okay. Yeah. Just.
Yeah, and I also had the related question to this slide related to Victor, to the fact that if you basically then you have this property, like the one which you wrote, the one on the TU, yes. But I wonder if there are other, the TUU equal T, yes. But I also wonder whether that there can be also other, because you have been also referring, I think, to other possible geometrical kind of representation, not only fish product, whether when you have some other invariances, right, not the first one which you had, but other ones in the slide where you had many properties, the invariances. Can you go to the invariances slide? This one. Yes. If some other, I don't know if you looked at them, but basically it's needs to be combinatorically somehow probably looked at, whether they will lead to some other properties, not the TUU equals T, but something else. if you know, if people looked at it. Do you know what I mean? Because basically you kind of described this theorem, some general, property of this ternary objects, but I wonder whether there are other properties of these ternary algebras that you could describe with that in this general form of the last theorem. If you go back to the slide with this theorem, because you were, this one.
So I think that there may be the interesting properties of this ternary product. So maybe this was the first step when I studied the question of Biunits. But I think there are more interesting properties in this ternary algebra which I have to study, and maybe I think I mean that my idea was that the ternary product, these ternary products, they are very fundamental, and the geometry, some geometric objects are like a metric, like invariants, can be generated by these ternary products of the hypermatrices. Mm-hmm. And maybe even this Biunit can also be interpreted in the framework of geometry, but I don't know how this can be.
Yeah.
Thank you.
Something in that direction. I don't know if you had seen I had a paper on Biunit pairs. Mm-hmm. So when you, instead of having a single, it's a very simple. Did you see it, Richard? So there's it's a very simple idea that you replace, instead of two elements being the same, you replace, and you have some u prime or ab or something, and then you look at the pairs as acting as a unit. So that equation, but having u and u prime for some other prime, and so I can send you the paper, because it's I did some work with an algebraist in Edinburgh a couple of years ago, and we found some really nice little theorems about these pairs. So essentially, we found them for semi-heaps. So these are closed algebras. So it's not exactly the same as these products, because obviously these products need some conformality conditions. But for square or cubic hypermatrices, like you might have here, there are some interesting results about, for example, if you have a biunit pair, so AB satisfy the equation ABX equals X for all X, it turns out that BA is also a biunit pair. So, and it turns out that if you have if there exists a B for a given A, for which AB is a biunit pair, then B is unique. So there's all these nice results about biunit pairs that generalize the notion of biunit element, which is just plugged twice, right? And so maybe that's another interesting way to sort of generalize this sort of environment. I find it super interesting, by the way, the fact that you're finding some of these invariants for this product is something that we thought about but never really did. And a direct way to generalize is to think of biunits. And so if I can give you my interpretation of the kind of thing that these biunit objects are, they seem to be, we thought of a generalization of so a semi-heap can be thought of as a heap can be thought of as a group without a choice of an identity, right? So of a neutral element. So it's essentially a group, and you can choose any element, and that element becomes your identity, right? So in the case of semi-heaps, we wanted to generalize, and so for semi-heaps we defined biunit pairs. So now you have two elements in the set. It could be the same by coincidence, so to speak, but they're generically two different elements. And then you said, well, what is the class of objects that have all elements be part of a biunit pair, in the same way that you would say that a heap is a semi-heap where all elements are a biunit in the usual sense. And so we know that there's a correspondence between groups and pointed heaps. So the idea was, what is the analog of pointed semi-heaps with Biunits, right? And we call these things die-heaps, as in double heaps or something, and we just don't know what they correspond to. It's an open question whether there's a family of. We know it's not groups because of these examples. Exactly, your work is showing there are examples of non-empty semi-heaps that have Biunit elements that are not just reducible to simply groups of matrices, right? So we know that there are more than just groups, but also we know that it contains all the group cases because of when you take the Biunit pairs be just two elements at the same time. So anyway, I'll send you the link if you want, because it's a very simple, very short paper. It's just some observations almost. It's not a very deep paper, but it has some interesting observations on Biunit pairs. Okay. Was there? I don't know if this was a natural conclusion point, or you wanted to mention something else. Otherwise, we can maybe have some round of questions if someone else wants to ask. Richard, do you have a question to follow up?
I already asked. Can you say again what a die heap is?
Yes. So a die heap. So a semi-heap is an algebra like the ones that have been shown here. That has
With
this,
the units.
maybe Victor had the axiom somewhere. There's the axiom.
Yes, semi-heap is a set equal to the ternary multiplication dots, which satisfies the generalized associativity of this kind. But look, when you shift these brackets to the middle, then these two second and fourth should be interchanged.
Yeah, so the middle one is U and, is that right? U and B are swapped, right? So the left side is ABC UV, the right side is ABC UV, but in the middle you have a UCBV, right? So U and B are swapped.
Okay.
So you can get that behavior exactly if you define, given a group, for example, or given matrices, just usual matrices, you can define a product that is A times B transpose times C, or A times B inverse times C. That ternary product will satisfy that equation exactly. So, an algebra that just satisfies that is called a semi-heap. But if every element of that algebra has the Biunit property, which I think is the next slide probably, I think you had So if you have that property where EEA equals A for all A, right? That's called a Biunit element. Right, and so a Biunit pair is when instead of having EE, you have E1, E2, or EE dash something, two elements. Yep. And so a die heap. So a heap is a semi-heap where all elements are like E, and a die heap is a semi-heap where all elements belong to a Biunit pair. So there's essentially a map that, given an element, will give you its companion. And they too make a Biunit pair. Okay. So that's a die heap. And so the open question is: so we know there's a theorem from Wagner in the 50s, I think 50s, 60s, that they proved that heaps are equivalent to pointed heaps. So a heap with a choice of an element is equivalent to a group. It's basically the same specification.
You're just choosing the identity there.
Exactly.
Okay.
You're just choosing the identity, and then you put in the identity in the middle of the product, and that ternary product becomes binary. That's your group operation. So we define die heaps, and we show that they are non-equivalent to heaps, and they are non-empty. So we know that they, and in this talk we saw some examples. So the question is, what is the group-like analog of die heaps? If you choose a Biunit, what kind of thing do you get? And we got some partial results, but nothing sufficient to find some. I mean, we actually found the correspondence. The correspondence is some kind of generalization of involutive semigroups, but it is a little bit baroque. It's what we call a switch semigroup, but it's a little bit baroque to. I don't know, maybe you like baroque aesthetics. You like it, but yeah, I can tell you more later. Yeah.
And
No, thank you, Carlos, because this notion of a pair of Biunits is very interesting. So it's a more general approach than the simply Biunit.
Yes, and it's very natural. So I will just show you very quickly. Oops. Bye. So this is being published now. I mean, I'll just give you the archive because the archive is the same. So I'll post the archive on the YouTube for people watching. Oops. Oh, there it is. And I'll post it on the Zoom so you can see. So you will see I did with my colleague Bernard Rimolovic. He's now at Heriot-Watt in Edinburgh, and I was at the University of Edinburgh at the time, so we made a little collaboration about semi-heaps. You will see that the biunit pair is a supernatural concept. It is very sort of self-selected. It just cries to be defined, and yeah, it'll be great to discuss sometime in the future when you think about it, what you think, because what you find, because we basically got stuck trying to identify these die-heaps, these generalized semi-heaps that are between a heap and a semi-heap, and there seemed to be something in the middle that we were. So yeah, it's an interesting thing.
Yeah, I see. This is a very interesting paper. Biunits, pairs, and semi-heap unassociated semi-groups.
Yes. Yeah. So
Thank you.
Yeah. The gist of it, just for because. So just to give you the point of it, because it will be, so if I get into this thing, the whole point is we find, let me see if I can find the equation. So die heaps are in correspondence with a kind of generalized involuted semigroup. So they are, we know they are in correlation with some binary structure, but which generalizes groups in particular, generalizes involuted semigroups, which is a bit more general. And so this is the condition. Wait.
Which one?
This one. So switch, we call a switch. It's a name for a map. It's in a semigroup. So it's this definition basically. So it's a semigroup with a map that behaves in this way, which is a little bit baroque. Let me make it bigger. It's a bit baroque.
Now I see. Yeah, now I see. No.
Yeah, but you can basically see that it behaves as if it were an involution and a homeomorphism, right? But it's neither of those, right? It's neither a homeomorphism nor an involution.
Yes.
You kind of assume that it works as a homeomorphism and an involution without assuming it's one. So obviously, an example of this is an actual involuted semigroup where the map is just the actual involution. So you have this relation here. Right?
Yes. Yeah.
But anyway, yes, it's a very simple paper. So I'll look forward to hearing what you think, because I think there will be some interesting follow-ups. All right, everyone. Any more questions?
Maybe just like a general approach one for all of you, maybe. Is it always possible or useful to describe these ternary structures in terms of binary ones?
Good question. Victor, you want to answer first? You heard the question?
But I didn't hear the questions.
You didn't hear the question?
Yeah, I didn't hear the question.
Okay, I'll repeat.
Can you repeat it?
Yes, I'll repeat. So Manu here was asking, is there a way to always express, right, the ternary operations in terms of binary operations?
And is it useful to do so?
And is it useful to do so?
No, I don't think so. No. We have so we have non-trivial ternary products which can be constructed by means of the binary products. So no, it's not reducible, not always reducible. Mm-hmm. So of course it's a very wide class which can be reduced to binary expressed with the help of the binary operations, but generally not.
Yes.
No.
So actually the products that Victor was showing today, which were the fish and this twisted fish, they already tell you that that's not quite the case, because even though you can express them as A times B transpose times C. That's not just a binary operation. It's a binary and a unary operation. You have the multiplication and the transpose, right? So already in this very simple example, you see that the ternary product, I think the fish is the easiest of all the ternary products in a sense, because it's the closest to the familiar territory. Already in this case, we see that it's not that the ternary decomposes into. And I think there is some theorem in what is called the N group or P group or p-adic group, sometimes literature, about general P groups, so associative P-area associative operations. There is some result there that tells you that when you introduce a unit element, you automatically collapse into a composition of binary operations. So essentially, the moment you have an identity element, you can put it in between the ternary product and you get a binary product. Okay. So when the operation is associative, and there's some condition I can't remember, you can always decompose any NRE operation into a lower arity operation. But this is only when you have associativity. So strong associativity, meaning that you can associate all brackets, and you introduce identity elements in the usual sense, in the traditional sense. So in that way, you can reduce. But by the way, none of the products that Victor or Richard have shown today with this hypermatrices, none of them satisfy associativity in the usual sense. This is something that I think we didn't mention that much, but because we are very used to this fact, but none of these products are nowhere near associative. I mean, the closest is this fish thing, this is semi-heap, which is kind of like a twist of associativity. But that's the closest thing we have. Everything else is unknown, what kind of properties they satisfy. Like this Jacobi, we don't know. Associativity, we don't know. I mean, we know it's not associativity, but we don't know if there's something like associativity, but higher order. And yeah, it's a mystery still.
Yeah, Carlos, I would like to mention a very wide, a very large class of so-called Ternary Lie algebras, which were introduced by Filipov. And yes. So in these algebras, we have an Ternary operation which constructed in this way that you cannot reduce it to a -1 or ternary to binary, because they use some kind of an approach of Jacobian. You have an element and the derivation in algebra, and then you write in a Jacobian. This cannot be reduced to a binary. No, it's a very wide class of.
Correct. That's an excellent example, Victor. Actually, just before your talk, we were talking about this Filipov algebras. The name Filipov is written on the blackboard here, actually. So, actually, that's a very good example. And even though Filipov algebras might sound a little bit esoteric for those of you unfamiliar, you actually already know Filipov algebras, what people call the affine Filipov algebras. So you know how you have you know how you can define the cross product in 3 dimensions with the determinant formula. You put exactly and so on. So you can imagine that formula actually doesn't care about dimension. So if you go 1 dimension lower, you have ij and then just 2 entries, which will be 1 vector. That's the complex structure, right? It's like the complex rotation by 90 degrees. But if you go 1 dimension higher, you go to 4 dimensions. Now you have whatever A1, A2, A3, A4, and then to complete the square, you would need 3 rows, right? Yes. So that's that ternary product in 4 dimensions, and that product satisfies exactly that formula, the Filipov condition, the Jacobi identity condition, and that is absolutely not reducible to any. It's like saying the cross product is reducible to something that is composition of unaries or something like that. It's not at all. So yeah, and each dimension has at the top at the sort of top -1 dimension, you have at n dimensions you have an n-1 array Filipov algebra. And so in n equals 3, that's the cross product, the familiar cross product. In n equals 4 is this ternary one that we studied a little bit, but in all dimensions you have this. And these are all inequivalent to anything known. These are their own algebras. They are their own thing. Yeah.
Yeah, that's a good example of this extension of the cross product to higher dimensions.
Yes, it's a very nice example. I like it. Yes. And I complain with because many physicists and many mathematicians say there's only a cross product in 3 dimensions and 7 dimensions. No. There are cross products in all dimensions. You call them differently. Yes, it's funny.
Is there a sense to thinking about heaps with just left or just right Biunits?
I will repeat the question just for you to hear, Victor. So the question was, is there a sense in which it makes sense to think of of heaps with either, or well, semi-heaps with either left Biunits or right Biunits? And do you have any examples maybe of what these things mean or represent? I personally don't.
No, I don't. No, I don't have these examples. No.
No. This. Yeah. And actually, in the I think it was in the paper that you mentioned, Victor, about the heaps of fish paper. You see this. I will share very quickly because it's a way to understand semi-heaps, or actually heaps, is that any if you're in a groupoid, are you familiar with groupoids at all? Okay, so groupoids are this relaxed version of a group. So basically, when you have group-like behavior, but you don't impose that all elements must multiply all elements. Okay. Are you familiar with categories a little bit? Yeah, so a groupoid is a category where all morphisms are invertible.
Okay.
That's it.
The question size.
So basically, so Victor, this is where we quoted your paper in our so we can quote each other. And so there's this section about heaps. If you're curious, I think this is a good reference to get a sense of heaps. Yeah. And my summary of heaps conceptually was this diagram. So basically, when you have a groupoid, which is a category where all arrows are invertible, if you take an object and you look at all the arrows that go from the object to itself, because you're claiming that all arrows are invertible, the set of all arrows that go from an object to itself is a group. And that's what people call the isotropic group or the vertex group or something like that of a groupoid. Okay. And so this is very well known in the literature. Everyone thinks of groupoids as essentially connected groups by a network of, so that is not necessarily on a single vertex, right? It has more than one center. So that's a good way to think of groupoids. A groupoid is kind of like you take the identity and you kind of blow it up to several identities, and then around each identity you have a little group. So the observation that I did in this paper is that if you, instead of considering the arrows from an object to itself, you consider the arrows from an object to an object, different objects, the structure that you get in the space of arrows is that of a heap, in fact. So in the same way that you get the structure of the algebraic structure of a group in the arrow set of an object, you get the structure of a heap in the arrow set between two distinct objects. So obviously, if you put the same object twice, you get the heap that will give you the group that is the thing. But if you don't, then you actually just have a heap in general that will give you that operation. And the interesting thing is that obviously there is no choice of, so here the left and right Biunits are given by identities on one object or the other. So they are actually separate.
Right.
So I'm not giving you much of an example, but I'm giving you sort of what I think is the natural space for these things to happen. And if you're ever, maybe you've heard of dagger categories before. So dagger categories are actually the natural environment of semi-heaps, because the most minimal example of a semi-heap is this construction where you have two objects, A, B, and then you take three morphisms, F, G, H, going in the same direction. And then you reverse one of them with a dagger, and then you can compose in a zigzag diagram, right? So you end up in B from A to B. So that composition satisfies precisely the semi-heap axiom by the axioms of categories and daggers, right? Cool. So if you ever want to think of semi-heaps in a concrete sense, you can always think a dagger category. Every morphism group, every morphism set of a dagger category is a semi-heap, canonically. So yeah, that's another way to say it. Anyway, sorry, that was just the context for the semi-heaps.
Let's thank Victor.
Yes.
For the brilliant talk. Thank you so much.
Thank you so much, Victor.
Thank you. Thank you. And please, if you want to put any papers also in YouTube, maybe from Victor, it would be great to have them.
Yes, send us the papers, and
you can maybe include them.
And maybe the slides as well, if you want. If you can send us the slides, people can have access to them. If you're happy to.
Okay, I will send this. Yes. Okay.
Perfect, Victor. Thank you very much.
Thank you. Yes.
Bye-bye.
Bye. And thank you, everyone. We'll see you tomorrow at the same time.
Bye, Olga.
Goodbye. Goodbye, James.
Bye, bye, bye.
Bye-bye.
All right. Bye, James. Thanks.